Okay, we are back. Happy Friday, February 19th, chapter 21. We gave a little intro to 21, talking about more nucleophilic additions to carbonyl compounds. Homework 6 for this chapter won't be due until next Wednesday, so you got plenty of time. We did grade homework 5 yesterday. And some people may have missed a point on number 47 if they didn't show structures. And it's okay to just discuss things, but if people just put down, oh, it's due to sterics or electronics or whatever, show some structures there. Show your work to get full points. Most people got tens and it was just fine, but I could look through and see a few that missed points there. So yeah, the graders, we need to see structures and see your reasoning there. Now don't go overboard on that. Don't write a big essay for each problem, okay, with a ton of structures, but show enough to justify it. And like I said, most people had it fine, but just a reminder there to be careful about that. All right, let's go up above here first. Look at the chapter outline again. Yes, we have 6 new reactions. We'll be doing cyanohydrins today with aldehydes and ketones. All these reactions are limited to aldehydes and ketones. The Wittig reaction with the Wittig phosphorane reagent, there's a new reagent for us. Aldehydes or ketones going to alkenes. And then imines and enamines from primary amines and secondary amines. And we'll examine the mechanism to see why there's a divergent mechanism and a different product here. Double bond between carbon and nitrogen, that's an imine. Double bond here between 2 carbons on the side, if it's a secondary amine. Okay, then we'll do hydration, and that will be kind of an introductory reaction. It's not really productive synthetically, but it's useful to talk about that reaction first before we get into acetals. And this is that key reaction, like we said, related to sugar chemistry. So that's our outline for it there. There's a lot of great examples, of course, of ketones and aldehydes. Let me just point out a couple here. Camphor, which is in a number of plants, has kind of that medicine-y smell to it that's in cough drops and a number of other medications there. Muscone, which is the male hormone of deer. Interesting compound. Cortisone, the anti-inflammatory steroid. Raspberry ketone, you can imagine where that comes from. And of course, practical things like antibiotics here. Oh no, it's glucose itself. You see the aldehyde right there. I'm not going to go through all of them, but each one of those has a very interesting story. And then the Hall of Shame. Some of these are toxic. Some of these are illicit steroids. This one's kind of interesting, diacetyl. That's responsible for a novel medical condition called popcorn lung. Now, a lot of you are going into medicine. Now, what would popcorn lung be? Well, this turns out to be the flavorant, the essence of butter flavor. And so you can imagine people who work at factories making those packets, those microwave popcorn packets. If they're exposed to this stuff all day chronically, they actually develop a lung condition. And it's medically accepted that this condition, deterioration of lung function, due to this compound right here, the popcorn butter flavor. And anyway, there's a number of other stories we could talk about, but we won't. Don't worry. I want to point this one out, though, an important application that we saw before, the vision thing here, and it's retinal here from retinol, which is vitamin A. It's a cofactor, okay? And it's first converted into the aldehyde. It's isomerized. And then it condenses with a protein called opsin. And this protein has a primary amine on it, one of the amino acid side chains. We'll see that later on as a lysine side chain. That primary amine can condense with this aldehyde and form what? Carbon-nitrogen double bond, an imine. It's a protonated form of the imine called an iminium ion. And that's the actual thing that undergoes the isomerization from the photon, from the light, okay? So part of the light harvesting mechanism involves this important functional group called an imine. Now, I warned you that in biochemistry, there's a number of intermediates, number of reactions that involve these reactions with nitrogen and oxygen nucleophiles that we'll be covering in this chapter. So I think that's good to review that. All right, let's get into Oh, one more to catch your attention here on the board. I don't know why I put on Xanax there. It's a sedative compound. You've probably heard of this drug before. Valium was the first one in the benzodiazepine family of drugs. Maybe you've heard about that in other classes. It's a GABA mimic. GABA, gamma aminobutyric acid, is one of the feel-good hormones in the body. This compound mimics that and actually binds tighter to the receptor and has a longer life to it. Why am I showing it here? What structures are present that might relate here to chapter 21? Can you see them? Well, benzene would have been for chapter 19, right? But what about this? What functional group is that? Carbon, nitrogen, double. That's what? An imine. Okay. In fact, the reaction we're going to cover actually follows that of how the drug's actually made. There's a imine right there. Is there another imine up here? Yeah, there's a couple more right here. I think that one is part of the synthesis of the drug, and then there's actually another one right here. Now that's a little bit different. This imine right here would come from an aromatic ketone right here, okay, and in the primary amine, okay, that's why it would be called an imine. And this one right here would be also a primary amine bonded to a nitrogen. That's kind of a hydrazone thing to form this triazole, this cyclic aromatic structure up here. And this carbonyl would be part of an amide. So that would be a different thing. It involves a different reaction that we haven't covered, but the carbon-nitrogen double bond you can call an imine. That's fine. All right, let's back up a little bit and do nomenclature. Okay. IUPAC nomenclature. We've been talking about aldehydes and ketones quite a bit, but we haven't done the nomenclature yet. Here's the basis of it. You take the E off the end and add Al. Okay. Now for an open chain acyclic aldehyde, the aldehyde carbon is always number one if you have other things on there. And then count up parent and count the carbon, just like we did for benzoic acids and carboxylic acids, right? We always counted that. So 1, 2, 3, 4. So this is what? Butanal. Okay. Now, yeah, and we don't need any numbering there. It's implied that the aldehyde is number one. How about this one? Now, this has an aldehyde and an alkene. Aldehydes have priority over alkenes, so we're going to name this as alkanal, but we can modify that name and include an alkenal. We can add an E right here for the alkene, but now we need numbering for where the alkene is. And what's the parent? That's the first thing to identify. 1, 2, 4, 6, 7. So what's the base name here? Heptane, heptanal, heptenal. Do you see the progression of the naming there? Heptenal. The aldehyde's implied to be number one. So what number do we need here to refer to the alkene? Well, it's 1, 2, 4, 5, 6. So that would be 6 heptene. And the 6 refers to the alkene part. And that's probably about as complex as we'll get with naming. Just to help you keep track of it. A couple other things to point out here. This is acetaldehyde. I won't draw out the whole thing. And that's kind of a common name. That comes from what? Acetic acid. Okay. Or you could call that ethanol. Okay. No chemist calls that ethanol. Okay. For ethane, we call it acetaldehyde. It comes from acetic acid. Okay. How about this one? This is a little different too, and we saw this with carboxylic acids. This is cyclo pentane carbaldehyde. I'm not going to draw out the whole aldehyde here, or carboxaldehyde. So cycloalkane and carbaldehyde, and that refers to the fact that the aldehyde has to be on the side. You can't have an aldehyde in a ring. Unlike a ketone, you can have a ketone in a ring, not an aldehyde, because you have to have at least one hydrogen on the side, right? Oh, there is another common one. I think we talked about this before. You could call that methanal, and that sounds kind of funny. What is that? That's formaldehyde, okay? So formaldehyde is another common name that I'm not going to draw all out. Formic acid, same root name, back to the Latin, whatever. So a little bit on naming there. Okay, ketones, you okay with aldehydes? Not bad. We're not going to drive you too nuts with that, I hope. How about ketones? Well, take the E off the end and add -one. And that makes sense. Ketone. So here would be a ketone. Let's name this one. And now, we can have the ketone at different spots on the chain. So we have to number them. And we give it the lowest number from whatever side in that's lowest, right? So this would be 2 what? 2, 1, 2, 6 hexane, hexanone. Okay. You could call this what? 2-propanone. Nobody calls that 2-propanone. In fact, the 2 might be redundant because if it's a ketone, it has to be at the 2 position on propane, right? What do we call this? It's not propanone. Well, on a test or quiz, you could say 2-propanone and get full credit. This has a common name, right? This is nail polish remover. Or what is it? Starts with an A. Acetone. Very good. Okay. From the acetyl group on a ketone. That's where it comes from. It's a contraction of that. But acetone. You're familiar with that solvent, I think. And it can be more complicated. So here we have what? A chlorofluoroketone. How are we going to do that? Oh, and a stereocenter. Ouch. What are we going to do here? Start with the base parent name, which is 1, 2, 4, 5, 6, 7. It's heptanone. And heptane. And at what number gets the ketone? And remember, the ketone has priority, so it gets the lowest possible number. So it's what? 1, 2, 3. And that 3 refers to the ketone now. Are we done? No. We got to do what? 1, 2, 3, 4 chloro. And then we got to do what? 1 fluoro. And we alphabetize those, right? So it's 4 chloro, 1 fluoro, 3 heptanone. But those are all the same ideas we've talked about before in nomenclature. Are we done? No. We got the stereocenter, right? So what do we do there? Put the lowest priority one in the back, which is hydrogen, and that's positioned in the periodic table, right, to get those priorities. Top priority would be chlorine, and then the carbon with 2 oxygens, and then that one. So what is that? Is that clockwise or counterclockwise? Clockwise, so we need an R out in the front. And there's only one stereocenter, so we don't need to designate the number. Okay, if we had multiple stereocenters, there would be numbers before each R or S. Okay, so yeah, it's a little more complicated with more complicated structures, but it helps you keep track of it. Now, there is another way to name ketones. You can name them alkyl, and I actually prefer this one for simple ketones. Alkyl, ketone. And the IUPAC will accept that, actually. The alkanone thing is fine. That's more thorough, I'd say. But alkyl ketone, what are we talking about here? Well, there's an alkyl group, and there's an alkyl group on a ketone. And you just alphabetize the 2 alkyl groups. So what would this be? This would be ethyl, and then propyl, and then ketone. Okay. So that's probably simpler, but what would be the more systematic IUPAC name for ethyl propyl ketone? Be 1, 2, 3, 4, 5, 6. It'd be what? 3 hexanone would be the more thorough way, I think. But anyway, questions on nomenclature? What if you have a cyclic one? Well, that's cyclohexane, cyclohexanone. Don't forget the cyclo, though, okay? And now, of course, the carbonyl can be in the ring, okay? But if we've got other groups here, we have to number them relative to the ketone, and the ketone would be number 1, okay? And the other groups, whatever. I think you can imagine some of those examples. Okay, questions on that? All right, let's get into the reactions. And first, I'd like to do a review of how we make aldehydes and ketones. And this is a good thing to review here because we actually know a lot of ways to do this. And, follow along here and see if you can draw in, the products here. What else do we have? Oh, acid chloride, lithium, aluminum, tri-TB-toxy. What else? Oh, how about a 351 reaction or two? Borane with an alkyne base. And, oh, a couple newer ones. How about this one? Cuprate one. And, oh, one more. Why not? Another 350 one here. Okay. To jog your memory a little bit and to review a couple of these real quick. We know a lot of ways to make aldehydes and ketones, don't we? Oxidation of alcohols, right? And if we use this oxidant, PCC, pyridinium chlorochromate, what do we get? An aldehyde or a ketone? What do we get? Aldehyde or ketone? From a primary alcohol with PCC, what do we get? Somebody says we get a ketone. Everybody agree with that? Aldehyde, yeah. So we stop at the aldehyde position. You can't get a ketone from a primary alcohol at all. It has to be secondary, right? You see that structurally? Yeah. How about methyl ester here with dibol? Diisobutyl aluminum hydride. What are we going to get here? Aldehyde or ketone? There's only two choices. You have a 50-50 guess for all these. What are we going to get here? Who remembers an ester with dibol? We're going to do a reduction, right? It's like aluminum hydride. But an ester, what? Ketone or aldehyde? Aldehyde, very good. In fact, it's the same one. That's easy. Okay. How about this one here? Lithium aluminum hydride tri-TB toxide with an acid chloride. So hopefully you're seeing a pattern here. Aldehyde or ketone? Aldehyde. In fact, again, it's the same one. Okay. We just have different approaches with different functional groups there. But, you know, remember those reagents? And looking at the structure, it has to be an aldehyde because it's on the end already, right? Okay. How about this one, though? Let's see, borane, and we're going to hydroborate, putting the boron on the end. So I'll get you started here with a little guess. And then we're going to oxidize the vinyl boron to a vinyl alcohol, and then it's going to tautomerize. And what's it going to tautomerize to? Oh, look at that, another aldehyde. Okay, so there it's the same thing. The electrophile goes to the N carbon. We've got an intermediate vinyl alcohol we got to remember. And tautomerization, we'll see that later on in a couple chapters. All right, now finally, it's all aldehydes up to this point, right? These last two, I'll give you a hint, are ketones. You got to come up with the structure, right? So acid chloride with a cuprate, tetrahedral intermediate, chloride comes off. So what's the ketone here? It's diethyl ketone. Or we could call that what? 3-pentanone, right? We did the IUPAC name. Okay. What about this one? Hydrating an alkyne. We're going to have a different electrophile now. We're going to put the electrophile in the end, which is going to be a proton with a strong acid. Water is going to attack here. We're initially going to get what? This vinyl alcohol, okay? And that's going to tautomerize. There's that term again. It's actually in this reaction and this reaction. And what are we going to get? We're going to get the ethyl methyl ketone in this case. Yeah, 1, 2, 4. Yep, 1, 2, 3, 4. Okay. There's a little review, and I like to throw in the 351 reactions to relate to that. Questions on those? Okay. And again, that's review. You can look those up in the previous chapters and see. Now let's get into the main event here. Our first new reaction, chapter 21, which is the cyanohydrin reaction. And we'll keep track of them here by the name, I think. But there are the 6, and we'll have to, you know, go through these systematically here. Cyanohydrin. Now that's kind of a funny term, hydrin, and we saw that before, and somebody brought it up in class the other day. Was it last time or Yeah, it came up. We were talking about chlorohydrins leading to epoxides. That's right. This hydrin term we've used for this reaction, chlorine or bromine with water, remember? And we get the chloroalcohol. And there, we called this a halohydrin. But look, the chloride and the OH group are on what, adjacent carbons. They're neighbors. We call these vicinal positions. Okay, vecinos, if you speak Spanish or Latin. What are vecinos in Spanish? Neighbors, right? So these guys are neighbors. They're on adjacent things. If you treat with base here, yeah, you can get the epoxide to form, and that's an intramolecular SN2 type reaction. So we saw the cyanohydrin name before, but here now we're referring to this, where we have a cyanide, okay, carbon nitrogen triple bond. I'm not drawing all the bonds there. And there's actually a lone pair on this nitrogen too. We've seen cyanides before when we use those as nucleophiles, and we are for this, but now it's with a carbonyl. And look, there's our alcohol again. That's an old word for alcohol, hydrin or hydrate, cyanohydrin. But look, the structure is different. These aren't vecinos anymore. These are twins. They're geminal, gemelos. What's gemelos in Spanish? Twins, right? Or Gemini for twins, right? And so they're geminal, they're on the same carbon, okay? So how do we get this? What's the main reaction here? Let's do it with acetone here and see if we can get this geminal relationship. The conditions is sodium cyanide and HCl. Okay. Now you have to be careful here. Cyanides are toxic. Okay. These are done very carefully. In fact, when we acidify any cyanide salt, we have the possibility of making HCN, hydrocyanic acid or prussic acid. That's a very dangerous material. If you inhale that, the cyanide will displace oxygen off the iron and hemoglobin, and you can asphyxiate yourself. Okay. So you've heard about hemoglobin. It's the transporter for oxygen in the body. There's a very high affinity for cyanide on that iron that's in the heme ring in hemoglobin. Maybe we'll talk about hemoglobin later when we get to biochemistry. But how does this reaction work? Well, cyanide, we've seen that before. We've seen that nucleophile before. Here's our electrophile now, right? Partially plus charge there. So let's go ahead and attack. Okay. So the mechanisms are all the same. All 6 reactions, the same as chapter 20, right? Just different reagents. So pushing the electrons up, what do we get? O minus and cyanide. It's already on there. What's the HCl for? How do we get to the neutral cyanohydrin? We've got a protonate. Yeah. So you can see why the HCl is in there. Okay. In fact, we normally add the HCl after the cyanide's been in there for a while. So maybe technically it's better to say that's a second operation. Okay. If you have it in at first, you might generate some prussic acid, some HCN, and that can bubble out of the solution, and that's where it would be a problem if you didn't have proper ventilation in the lab or whatever. But question on this? So yeah, the mechanism's pretty straightforward. So how about this one? Let's take benzaldehyde. So we just did a ketone. Let's do benzaldehyde and look at the benzyl cyanohydrin. So we got an aldehyde now. And by the way, all these reactions are specific for aldehydes and ketones. Of course, there are other carbonyl functional groups, esters and amides and a lot of others. All 6 of these reactions are specific for aldehydes and ketones that don't have an extra leaving group on the side, okay? These reaction combinations will give different things. So try to narrow down your focus when you work on, mastering these reactions. Don't try to think of every possible permutation. You'll see that on some of the harder problems where we give you a product, okay? But master the simpler substrates, aldehydes and ketones. And this is a simple aldehyde, right? Benzaldehyde. So what do we get here? The benzene ring, the OH, and the cyanide. Not drawing this hydrogen, it's there. You can see that came from an aldehyde because there is a hydrogen there, right? Okay, so it's that one. And let's see, maybe one more. How about this one? And how about this one? So yeah, I think you can come up with those, okay? Same conditions, so cyanohydrin. And now this is a useful reaction synthetically because we make a carbon-carbon bond again, okay? And a cyanide's a useful functional group. We can convert that to a lot of things we'll see later on. And so this one would go tert-butyl, OH, and cyanide. And that came from a ketone, right? So there's a couple more examples for you there. We should say that this reaction is reversible under certain conditions with strong base. It can be reversed. In fact, in nature, this one is found in pit fruits, in the pits of peaches and apricots and fruits like that that have the hard pit in the interior. And if you bite into that pit and start chewing on that softer part, the seed, you actually run into this phenyl cyanohydrin. And under basic conditions, that can reverse back and cyanide can be generated. Those are toxic, the interior of those pit fruits. Maybe you've heard that before, but yeah, but forming the carbon-carbon bonds, an important reaction. Questions on cyanohydrins? That's our first one, okay? So far so good, I think. Let's go on to the Wittig reaction now. This one's named after a person, Georg Wittig. And pronounce it correctly, he's German, so W is a V sound. Don't call it the Wittig reaction. We'll know right away that you're not an organic chemist if we hear Wittig. Okay, it's Wittig. In fact, Georg and H.C. Brown shared the Nobel Prize. H.C. Brown for hydroboration, the reaction we just did with alkynes up there. And Georg Wittig, I think it was 1979. They shared the Nobel Prize. These two reactions opened up a lot of new synthesis. And the Wittig reaction is based on the Wittig reagent, which is triphenyl phosphorane. So it's a carbon with an anion charge on it, negative charge. And the phosphorus of the Wittig reagent has a plus charge, okay? And this is called a phosphonium ylide. That's a lot of term, or phosphorane. Now, yeah, I'm going to point out some names here, and I'm going to use the names as I talk about it. On a quiz or a test, don't try to memorize all the specific names here for these different phosphorus reagents, just how they're used here. You should know this part, this ylide. This ylide refers to a specific type of ion called a Zwitter ion. And a Zwitter ion means there's a plus and a minus charge within the same molecule. A special type of Zwitter ion is called an ylide, where the negative and the plus charges are right next to each other. Okay, so it's a neutral overall molecule, but you can think of it as a carbanion with a phosphorus plus. The other thing to notice here is phosphorus is in the same family as nitrogen, so 5 valence electrons. Okay, so how do we get this plus charge? Well, 5 valence electrons minus 4 bonds. We're down to what, +1, and there's no lone pairs on this phosphorus right now, so it is +1. Okay, and then a carbon with 2 lone pairs and 3 bonds, and carbon has 4 valence electrons, right? So you should come up with this. This also has a resonance structure that looks like this, where the 3 benzenes and the phenols refer to benzenes. There's 3 benzenes on the phosphorus, and then we have a double bond on carbon and the 2 R groups. So sometimes we draw the phosphorane like that, the Wittig reagent, just like that, okay? Now, how does it work? Well, we react it with an aldehyde or a ketone, and we are just sticking with aldehydes and ketones. Make sure you're not experimenting too much with other functional groups, okay? There are some related reactions with other carbonyl compounds, but aldehydes and ketones helps you narrow the focus and think about this. So what does it give here? What's the product? What's this? It's an alkene, okay? And that's a pretty important reaction, I think. You can form an alkene. Di, tri, mono, tetrasubstitute alkenes, all sorts of alkenes. Where what? This was the carbonyl right here, whatever was on the ketone or aldehyde, right? And then whatever was on the phosphorane goes there, okay? So it's a very useful reaction synthetically. In fact, we call it the reverse of what? Reverse of ozonolysis. Now, it's a completely different reaction. We don't mean equilibrium here. We mean if you take an alkene and treat it with ozone, you go back to the carbonyl compound. Okay, so it's kind of the reverse of that. It's a way to think about it and relate it to what you know before. Let's look at some other examples here before we get into the mechanism. Of course, we will. How about if we take this cyclohexanone and treat it with this Wittig reagent? Now, it's not an equal sign. What do I mean? Well, that's that resonance structure here where the two R groups are just simple H's, right? Okay. So if we react it with this, and it's a pretty simple reagent, you know, the solvent has to be an inert solvent, no proton sources, usually THF, ether, or methylene chloride. So if I have this Wittig phosphorane, we're going to go to this product. You see, that's just the reverse of the ozonolysis, right? Now, that's kind of a unique looking alkene. We talked about a similar, an isomeric form of that alkene. We talked about this guy, right? And we made that from dehydration of this, right? We treated that with H2SO4. And how did we make this tertiary alcohol before? We made it from what reaction? Previous chapter. What was that reaction we were talking about there? How did we make that tertiary alcohol before? Starts with a G, Grignard reaction. Yeah, we added the methyl Grignard to that same ketone right there, right? And I said, well, we're not going to eliminate up here because that would violate Zaitsev's rule. Well, what if we want this alkene? Okay, that's the less substitute, disubstitute alkene. This is trisubstitute alkene. That's the thermodynamically favored one. This is not thermodynamically favored, right? But look, the Wittig reaction, wherever the carbonyl is and whatever's on your phosphorane, it stays put. It generates that type of product. So it opens up some complementary type synthesis routes that weren't available from simple dehydrations, okay? Let's see, let's get a couple more examples on the board here. How about this one? We can take, there's the condensed form of benzaldehyde, right? And let's react that with, let's see, oh, how about this phosphorane? Cyclopentyl phosphorane, okay? What are we going to get there? Well, we're going to get the benzaldehyde, our double bond, and then whatever was on the Wittig reagent, okay? So it's going to give that product right there. Okay, so there's a couple examples. We'll do a couple more. Let's get into the mechanism now. You can kind of see how it's going to work. We've got the phosphorane with a carbanion, a negative charge on the ylid. So that's going to be our nucleophile. Let's see what we do here. Let's do the one with acetone. We've got the triphenyl phosphonium, and then this guy, okay? Now you can use either resonance structure of the Wittig ylid. Let's use this one here and attack, okay? There's our electrophile, and this part over here is our nucleophile. So it fits in with everything we've talked about with nucleophilic addition. And then what do we get? We get O minus here, and we get the phosphonium salt still on there. And there was our carbon that was our nucleophile. So you can see we've already attacked here. We've made a new carbon-carbon sigma bond. How do we make the pi bond of the alkene now? And I'll give you a hint. The byproduct here, what we're going to generate from the phosphorus will end up as this. Triphenyl phosphonium oxide, or triphenyl phosphine oxide. Now that's a stable structure, okay? It's related to phosphates. It's got 5 bonds to phosphorus. And phosphorus-oxygen bonds are very stable thermodynamically. And that's a driving force for this reaction. This is why the alkene part of this reaction forms. We're going to form this triphenylphosphine oxide, or this phosphonium oxide, however you want to call it. These are just resonance structures of each other. So yeah, how do we get this oxygen then on phosphorus and then get an alkene right here? That's the tricky part now. What do I need to do? Well, this is within the same molecule. So we can form what's called the oxaphosphatane. I'm not even going to draw that name. There are names for all these things. This mechanism is well known now. The oxaphosphatane is a known intermediate. Now, you see, we've got this bond here, and we've just wiped out this zwitterion, right? This isn't an ylide now. They're not on adjacent atoms. But it is a zwitterion. We have a negative charge, a plus charge still, okay? And now we have a neutral thing here called the oxaphosphatane. And we've got the oxygen-phosphorus bond. So what can we do here? Well, let's just put this charge on oxygen right there, okay? And what? Let's put a plus charge on phosphorus. How do we do that? Right there. And it's known to be concerted. The collapse of the oxaphosphatane is known to be concerted. Let's see what the product looks like. Oh, well, there it is. It's the alkene, right? This methylene now is part of the alkene. There we form our pi bond. And what's our byproduct here? What comes off? Oh, yeah, O minus and phosphorus plus charge, okay? It's called triphenylphosphine oxide. But again, yeah, you don't need to worry about that. Okay, how about using now the reaction in synthesis? Let's give you a couple examples of alkene products and ask you if you can use the Wittig reaction to make these alkenes. So we're switching it around now. We've got this. Oh, that's our old friend styrene, right? The John Huntsman molecule. How can we do that? Well, let's zip this apart. There'd be 2 ways. One carbon then becomes the carbonyl, and the other becomes the Wittig reagent. Make sure you can do that either way. Let's see if we can do both here. So we could make that from the benzaldehyde plus what would be our Wittig reagent? Well, triphenylphosphine and then with an equal sign to a carbon. No, that's not an equal sign. That's what? Carbon, 2 hydrogens. I'll draw them in there just so you can see that. Okay. That's one way. What would the other way be? That would be where we'd have the Wittig reagent like this. Okay. And then what would be our carbonyl instead? We'd need to have this as our carbonyl with 2 hydrogens on it. So what would be the carbonyl? I need to draw here. Ah, what's the name of that? Formaldehyde, right? Okay. So either way, both of these routes would work okay. The cheaper one is actually this top one. That's readily available. You can easily make that. We need to talk about how to make the Wittig reaction. Let's look at one more synthetic problem. So how about this alkene? I'll zip it apart, and let's just do one. Okay. We'd have this as an aldehyde here on the left, and on the right would be our Wittig reagent. Yeah, make sure you have the phosphorus directly bonded to the carbon, and then the 3 benzenes on it, okay? So that would be one way to make that. Now, for the purposes of our class, we don't need to worry about E or Z selectivity. In general, the Wittig reaction actually gives Z selectivity, okay? There are ways to switch it over to E selectivity. I think that's beyond the scope of our class. If you want to make either one using a Wittig reaction, just make sure you correctly use a carbonyl and the Wittig reagent. And don't worry about cis or trans selectivity. Is that okay? Can I make a deal with you? let you off the hook there. Okay, I think everybody was in favor of that. Okay, but there are ways to figure that out. Okay, but we'll leave it at that. Let's get into the synthesis of the Wittig reagent, how it's actually made. And this is important to know. On a quiz or a test, you might be asked to show how you make the Wittig reagent you're using. Okay, so let's see. Let's make a Wittig reagent that's going to have 1, 2, 3, 4, 5 carbons on it. They always go back to alkyl halides. Okay, and the first reaction is triphenylphosphine. There's another term, I could write it on the board, triphenylphosphine. It's analogous to amines, the nitrogen analog, which is trivalent, right? But there's a lone pair on trialkyl or triaryl phosphine, right? So there's a 5 valence electrons, right? So there's a lone pair here. And what do you get here? You get SN2 chemistry. This is actually a very good nucleophile, okay? It's lower in the periodic table. These lone pairs are held further out from the atom than even amines. They're better nucleophiles than even amines themselves. Remember, he said neutral amines could be good SN2 nucleophiles. So it is really primary is faster than secondary, whatever. But this is the key one, I think, for looking at this. So we have triphenyl phosphonium bromide now. I just used another term. Phosphonium is the same as ammonium, which is what? Tetravalent nitrogen, right? Protonated nitrogen or protonated amines. Or tetraalkylamines are called ammonium salts. Well, this is phosphonium now. That's a salt material. There's a lot of them available commercially, so you can often buy the Wittig salt. This is called the salt form. Notice that's not the Wittig reagent yet. What do we need to do here? We've got 2 hydrogens here. We need the ylide. How are we going to get the ylide now? We need to have a carbanion here, right? What do we need to do to the salt to get the active Wittig reagent? We don't have it yet. What do we need to do? Do we need to use a base or a acid or a radical reagent? What do you think? Who votes for using a base in this case? 1 guy, 2 guys. Who says we need an acid there? Okay, nobody on it. You're right. The base people were right. And the base we're going to use, we'll stick with the one pointed out in the book. This is butyllithium. Boy, that's one of the strongest bases we know. You have to be very careful with that. Butyllithium is butyl lithium organometallic, carbanionic at this carbon, right? Plus charge here, negative charge here. That's going to grab a proton and leave behind the electrons. Okay, very strong base. So you're correct there. And notice that will give us the ylide. So then we'll have our triphenyl phosphonium ylide. And I'll just draw it as the neutral form there. I'll collapse that. And so the lone pair here can just dump in here and form that double bond between carbon and phosphorus. That's okay. You can go up to 5 valencies on phosphorus because it's a bigger atom. And what's our byproduct here of the butyllithium? It's butane. Okay. And you can remind yourself the pKa of an alkane is 55. That's super weak acid, which means what? Its conjugate base is super strong, right? The pKa here is known. It's about 20. There are other bases you could use, but we'll stick with the one that's in the book, butyllithium, okay? That simplifies things too. But you have to show that. And now what? Oh, let's do maybe cyclopentanone and do the Wittig reaction. So we get cyclopentanone alkene now, and then how many carbons on it? 1, 2, 4, okay? So that came from the Wittig reagent, right? 1, 2, 3, 4, 5. Yeah, we had the 5 carbons here to begin with, and we wind up with 1, 2, 3, 4, 5 there, okay? But you can see how it's used. This is the actual Wittig reagent now, and these steps here show how it's made, okay? Questions on that so far? All right, not too bad. Again, we're not going to worry about cis or trans in cases, okay? Normally it is the cis that's favored about 10 to 1, but there are ways to add different things and adjust the temperature to get it to go over to the thermodynamic trans product, but we're not getting into that. Okay. I think it's enough to just go through the Wittig reagent and the simpler reactions. Is that okay? Questions on that? All right, now before we get into imines and enamines, I'm going to do a little review of equilibrium. So these are both carbon nucleophiles that we just did, cyanide and the Wittig reagent. These are carbon nucleophiles. Now we're going to get into nitrogen, imines and enamines, and oxygen for the acetals, okay? These have lone pairs, and they're neutral nucleophiles to begin with. And they're going to make carbon heteroatom bonds, right? So some things we need to talk about here. So these nucleophiles are, in general, going to be weaker. Let me just abbreviate them as, nucleophile with, at least a pair of electrons on them. Okay, the electrophile will be aldehydes or ketones, and we'll stick with aldehydes and ketones. What is our product here? Well, it'd be O minus and maybe plus here. And, how favorable is this? Is this reversible? Well, it could be. And we'll see a lot of cases, especially with the hydrates, where it's freely reversible. The products aren't favored at all. But we can make these, geminal hydrates that we'll see later on. But now, there's going to be something else here. We can transfer, protons or whatever and get, the neutral thing. And maybe we had, a proton on here to begin with. So, I'm not trying to be fully generalized here, mechanism thinking about. But here we're going on to another product, right? In fact, we can think about going on to yet another product here, okay? This double bond, the imine idea, okay? Then we're going to have to lose, water maybe. Well, let's look at this equilibrium here just at the beginning. So we can draw any K for any reaction, right? We did Kas before for acid equilibrium and water, right? Those Kas are a little bit different. But we can draw a K equilibrium for any reaction here. And let's just say product overall. And our product might be this, or it might be all the way down here, right? But the product concentration at equilibrium would be what? In the numerator, right? And this would be times, let's see, if we're losing water, right here, that might be a byproduct. That would be in the numerator also, right? And then what would be in the denominator here? We're all starting material, our carbonyl compound, and maybe whatever our nucleophile is. That would be the general thing. Now, to tell you, and you might be disappointed to think that a lot of these reactions we're going to show, the initial step is often not favored at equilibrium. In fact, it might just be a part per 1,000 or 10,000 present. So it might be highly unfavored, this equilibrium, to start out with. But look, if there's something down the line here that's favored, and we go to a lower free energy point in the final product, what does this do? This allows us to overcome this unfavored equilibrium. So don't worry about this if this arrow might be going back the other way. What we can do here, right? We can, by Le Chatelier's principle, adjust this system in order to favor product. That's what we want, right? What can we do here to maintain this K? Mathematically, that's what it is. But it's an overall system, right, that's dynamic. So what can we do here to boost the concentration of the product and keep K happy? Take out water. So that would be this, right? And mathematically, you see, if this is going way down, what's going to happen to our system? This has to go up. So very good. So if we dehydrate it or remove water, we'll see that, in the imine and enamine reaction and the acetals. A couple other things we could do here, right? We could boost the amount of starting material. That's how metabolism works. When you bring in nutrients, whatever, higher concentrations of those precursors, the different things in the body, glucose and producing all the byproducts, pyruvate, acetyl-CoA, and things you may have heard about. So it's an adjustment here. If this is boosted, This has to be boosted to keep K the same, right? Same thing here, our nucleophile. We could increase the concentration there. So you see, we can increase anything in the denominator to boost our product, or we decrease the other thing in the numerator, right? Mathematically, you see how that might work? And then chemical-wise, this is being pulled out. It pulls the equilibrium toward the product, even though this may not be favored, okay? So it's something to keep in mind. And yeah, we're out of time. But here's our first reaction, our imine reaction. And the imine and enamine thing is a little bit tricky, but here we're talking about primary amines. And when I say primary amine, what do I mean? Amine, imine, a lot of means running around here. Primary amine is just one alkyl group on that nitrogen. And what this is going to form is this. Okay? That's called what? The imine. Okay? We'll get into that next time. We'll do the mechanism and justify that. And we're going to do the same thing here, but we're going to use a secondary amine. Yeah. Do you see why that's a secondary amine? We have two alkyl groups on it now. So diethylamine versus just regular ethylamine, or any other variations. This will give us what now? This will give us the enamine. Okay. And it'll come out of the mechanism. You'll see why the difference between imine and enamine next time. We'll go through the mechanism, but yeah, the first step's actually reversible, but because of the elimination of water in a couple different places, we'll give the right product. I think we're good there. Questions real quick? Sorry. Got time? No, we don't. Come down if you got a quick question, and we'll see you guys on Monday. Yeah, very good. Thank you.